Have you ever stopped to think about how a firework just explodes in this brilliant flash, but then an old iron gate takes years and years to rust? I mean, they're both chemical reactions, right? But they are running completely different races. Some are these lightning-fast sprints, and others, well, they're more like ultramarathons. So let's get to the starting line and figure out what's actually controlling the pace here. Yeah, that's the big question we're going to tackle today. What are the secret controls? What are the dials and levers that dictate whether a reaction happens in the blink of an eye or over the course of a lifetime? And, understanding the speed of these reactions, it's not just for chemists in a lab coat. No way. This is the key to everything from cooking your dinner faster to designing life-saving medicines. It's really all about learning how to control the race. Okay, so before we can start messing with the speed, we've got to understand the fundamental rules of the race. What even is the rate of reaction when we talk about it? Well, to put it simply, it's just a measure of speed. It's how quickly our starting ingredients, the reactants, get used up and how quickly our final stuff, the products, get made. That's it. So the key here, the master rule book for all of this, is something called collision theory. And it sounds pretty simple, right? The theory basically says that for a reaction to happen, particles have to physically collide. They gotta bump into each other. But as you can probably guess, it's not quite that simple.
See, not every little bump actually leads to a reaction. I love this analogy. Think of it like a very, very specific high five. First, you've got to have enough energy, right? A weak little tap just isn't going to cut it. And second, you have to hit each other in just the right way. Palm to palm, not, palm to elbow. You need both enough energy and the correct orientation for that collision to actually cause a reaction.
All right, now that we know the rules of the game, let's get to the really fun part, the control panel. Let's start looking at the actual dials and levers we can pull to speed up or slow down any chemical race we want. So our first dial is temperature, and cranking up the heat, it's basically like giving every single particle an energy drink. They start zipping around way faster, kind of like a bunch of kids running wild on a playground. And what happens then? Well, they're going to bump into each other a lot more often. But hold on, it's not just about more collisions. Because those particles are moving so much faster, they're also hitting each other harder. And that means more of those collisions are going to have enough energy to be successful. So it's a total double whammy, a real win-win. Okay, next up on our control panel, concentration and pressure. Just imagine you're at a party, right? If there are like 5 people in this huge empty room, you're probably not going to bump into anyone. But what if you cram 100 people into that exact same room? Yeah, collisions are pretty much guaranteed. And that's the whole idea behind concentration. And for gases, pressure works pretty much the exact same way. When you squeeze a gas under high pressure, you're just forcing all those particles into a smaller space. You're crowding the party. They have no choice but to run into each other more often, and boom, that speeds up the reaction. So our third factor is surface area. And here's a perfect example you see every day. Why does granulated sugar dissolve in your coffee like instantly, while a solid sugar cube takes forever? It's because you've exposed way, way more of those little sugar particles to the hot water. It's the same amount of sugar, sure, but you've given it tons more surfaces that are ready to react. Yeah, think about it. In a solid block, only the particles on the very outside can get in on the action. But the second you break it up, all those particles that were trapped on the inside are suddenly exposed and ready to join the party. More available particles means a much, much faster reaction. Okay, so we've been talking a lot about the energy of these collisions, but let's try to visualize what that actually looks like. It turns out every single reaction has to climb over this kind of energy hill just to get started. And this energy barrier has a name. It's called activation energy. A really great way to think about it is the push you need to give a skateboard to get it going, right? Once it's over that initial little hump and it starts rolling, it can keep on going. Well, a reaction needs that exact same kind of initial energy investment to make it over its hill. Now, once the reaction gets over that hill, some of them, they release a ton of energy. Think of a bonfire. If you look at this graph, you can see the products at the end have way less energy than the reactants had at the start. So where did all that energy go? It was released as heat and light. That's what we call an exothermic reaction.
And the exact opposite of that is an endothermic reaction. The perfect example is one of those chemical ice packs you snap. It actually has to suck in energy from its surroundings to even happen. So if you look at this graph, the products finish with more energy than they started with because they've absorbed all that energy from the outside. And that's exactly why an ice pack feels cold. It's literally stealing heat from your body.
Okay, now let's tie this whole energy hill idea back to temperature. So at any given temperature, all the particles in a substance have a range of energies. Some are kind of slow, some are super fast. That vertical line on the graph, that's our activation energy. Now watch what happens when you increase the temperature. The whole curve shifts to the right. See that? That means a much, much bigger chunk of your particles now have enough energy to get over that hill. This is the visual proof for why adding heat is so effective. But what if you can't just crank up the heat or add more pressure? What if you need a smarter, more clever way to speed things up? I mean, this is absolutely crucial for everything from giant industrial processes to the tiny little enzymes in our own bodies. Well, that's where our final factor comes in. And trust me, it's the ultimate game changer. We're talking about a catalyst. A catalyst is kind of like a chemical matchmaker. It's really cool. It doesn't actually get used up in the reaction itself. It just helps it happen faster. Think of it like a coach. The coach doesn't run the race for you, right? They just show you a smarter, easier shortcut to the finish line. This is exactly how the catalytic converter in your car works, or how the enzymes in your stomach digest your food.
And here is how it works. This is the genius part. A catalyst doesn't give the particles more energy. No. Instead, it actually lowers the entire energy hill. See that dotted line on the graph? That's the brand new, easier shortcut the catalyst creates. By providing this shortcut, way more particles can make it over the top with the energy they already have. It's brilliant. Whew. Okay, we have covered a lot of ground here, from crowded parties to energy hills and chemical shortcuts. So let's pull it all together in one final, super clear summary. And here it is, your very own reaction control panel, your cheat sheet. If you want to make a reaction go faster, you can increase the surface area, crank up the pressure, boost the concentration, or raise the temperature. Or for the ultimate shortcut, you bring in a catalyst to lower that energy hill. These are the 5 fundamental levers that let you control the speed of the entire chemical world. So the next time you're cooking something or you see a piece of metal starting to rust, you'll know exactly what's going on behind the scenes. And that leaves us with a final thought, right? If you had this control panel in your hands for any reaction in your daily life, what's one thing you'd choose to speed way up and what's one thing you would slow right down?